Okay, yeah. So we are trying to show why the integral test is true, meaning that both the series converge, both the series and the integral converge or diverge. We're kind of comparing a series to an integral. And I am trying to find bounds for our partial sum, for our, yes, partial sum. This is a, for our integral, okay? By just looking at these pictures. So we said the integral from 1 to n, which is area under this curve, is larger than the sum of the area of these rectangles. And that sum is just basically the sum of the terms of the sequence from A2 to A sub n. As you saw, every one of these rectangles is just the same as the term, as a term of the series. Okay, so since these rectangles are inscribed, they're below the curve, then the actual area is more than the sum of the area of these rectangles. Okay, now we can find a right bound for our integral from 1 to n, using this picture, since these, and that's because these rectangles are circumscribed, they're above. They are above the curve. Okay, now the area of the first rectangle is the same as length times width. Here length is A1. This is the length, and that's the same as the first term of the sequence. Width is still 1, so we get A1 plus the area of the second rectangle. The length of that rectangle is the same as the second term of the sequence, which is A2. So we do A2 times 1. That gives us A2 plus A3 plus the length of the last, or the area of the last rectangle, this rectangle, is A sub n minus 1. That is the length. Again, we are taking the left endpoint of each subinterval. For n minus 1 to n, we take n minus 1. So an minus 1 is that area. Okay, and we can write that in summation form as the sum of a sub k, where k begins with 1, ending at n minus 1. Okay, so our integral, this integral, is less than this sum.
I have a question.
Yes.
I'm pretty sure I explained this last time, but why is k equal 2 on the other one, in the blue series?
Yeah, that's because when you look at the first rectangle, here's the first rectangle. The way this rectangle, let me zoom in, the way this is drawn is that you take, you draw the length starting with n equal to 2. See, you go,
right, okay.
Yeah, you got the 1, you got the 2, you start from 2, you go up, so you hit A2 right there.
Okay, that makes sense. Thank you.
Okay. All right. So this is an inequality that we just established, and let's see what this has to do with what we can do. What we can do to it to prove the integral test. Okay. Yeah, so there are two inequalities. We have this inequality here. Call this the first inequality, And this is the second inequality. We're gonna work with them separately. Let's see what each of them imply. Okay, so let's go with the first inequality. I'm gonna copy this down. And I'm not gonna, should I use colors? No, I'm not gonna use colors. So first inequality, which says that the sum k from 2 to n of a sub k is less than the integral from 1 to n Okay, now our series starts with 1. Okay, we're trying to prove the integral test. If you look at it, again, the series begins with n equal to 1. Where is my integral test theorem? Right here. Yeah. So I have to make an adjustment to this inequality so that the series begins with 1. I want this to begin with 1. I want to have that consistency. Okay, would you please mute yourself? If it's you, Alex. Alex, thank you, Alex. To make this begin with 1, just add the first term, no problem. Add the first term, a1, to that sum. Okay, so I'm just gonna do a1 plus the left-hand side of the inequality and also do a1 plus the right-hand side of the inequality. It's an inequality. You can, by properties of inequalities, add or subtract a number to or from both sides of the inequality. Okay, and the inequality doesn't change. So now this total, you can write that as summation k from 1 to n of a sub k, and that's less than a1 plus the integral from 1 to n of the function. Okay, so we did that adjustment. Starting the sum with 1 means that you have to add a1 basically to the right hand side. Okay, now we are trying to prove something about the sum, the infinite sum, the series. And for the series, we have to take n to infinity. So by the way, this thing holds true for all n. Okay, this inequality is going to hold true for all n, and that's because the function is decreasing. Okay, the function is decreasing. This sum is definitely going to be less than sum. If the function is decreasing, then all of these rectangles are inscribed. They're all below. So the area, the total area of these rectangles will definitely be less than the actual area. Okay. So yeah, this holds true for all n. Therefore, we can take the limit as n goes to infinity. We have the limit of the left hand, which is the limit of that sum. Okay, and take the limit of this whole thing. Well, the limit of a constant is constant. Okay, the limit of a1 is just a1. Okay, and we have to apply the limit to that integral. Okay, now we have, what is Nicholas asking? Can negative and increasing function apply to integral? No, definitely not, Nicholas. Definitely not. If the function is increasing, then this is not going to hold. Okay. Yeah. So guys, now we have, if you notice, on the left, we have the definition of the series. A series is the limit of a partial sum. This is our partial sum. This is the partial sum, not my partial sum. The partial sum of the series, you're taking the limit of that. So you get the series where k goes from 1 to infinity of a sub k. Okay, and that is going to be less than a1 plus, this is the definition of an improper integral. That's the integral from 1 to infinity of f of x dx. Okay, so we just established this wonderful inequality. This is, guys, this inequality is so cool because, well, actually, let me see, this inequality right here, or either this one or this one. These are cool because they give you an upper bound for your series. Okay, if you don't know what the value of your series is, assuming your series is convergent, if you don't know the value of the series, then you can come up with what with the upper bound. Upper bound is the number that the series can't exceed. Okay, so whatever the series is, that series, assuming again convergence, is always going to be less than the first term plus the improper integral. I'm going to be showing you how to use this inequality later. Okay, but this inequality is true. Now, assume that the integral, so here is the conclusion. This is how the conclusion plays out. Assume that the integral is convergent. Okay, which means the integral from 1 to infinity of f of x dx is equal to some finite number. M is just some finite constant. Okay, so what we get here is the series, k from 1 to infinity of a sub k being less than a1 plus that number m. Just think about this result for a second. This is telling you that your series, your infinite series, is less than finite. Imagine a1 is 1 and m is 10. If your series is less than 11, then there is no way the series is going to be infinite. There is no way it will diverge. It has to converge. Anything less than finite must be finite. It can't be infinite. Therefore, is convergent. Does that make sense? Oh, Ahmed, guys, look at what Ahmed is saying. Ahmed is asking, does this basically say the series approaches a1 plus m? No. No. We don't know what the series approaches. We don't. A1 plus m is the number that the series is not going to exceed. Okay, the value of the series could be, a1 plus m could be 11, but the value of the series could be, in reality, 10.1. Okay, a1 plus m. We don't know what the series is going to. We haven't found the actual value of the series. That's just a1, first term of the series plus the value of the integral. They're not equal. Remember, the integral, this area, and the sum don't have the same value. Okay, we have these errors. They differ by the sum of these errors. Okay, but in any case, anything that is less than finite has to be finite. Make sure you understand what we just said here, because this concept will be applied later to what's called comparison test. Finite, this is less than finite, so this has to be finite. Okay, this is just an upper bound of the series. So this was the part for the convergence. Well, what about divergence? We haven't proved the fact that if the integral diverges, then the series is going to diverge. For that, we are going to take the second part of the inequality. So again, this was the first inequality. Now let's write down the second inequality. Okay, and the second inequality says that this integral is less than, where is it? Yes, the integral is less than the sum from 1 to n minus 1. Let me copy it down. So the integral from 1 to n of f of x is less than the sum k going from 1 to n minus 1 of a sub k. Okay. Again, we have this inequality, and it is true for all n because the function is again increasing, meaning that the sum will always be greater than the integral. Okay, so once more, apply the limit. We'll do limit of the integral. And that is going to be less than the limit of that partial sum. Okay, so again, on the left, the limit of that integral is just the definition of the improper integral from 1 to infinity. And on the right hand, you also have here, well, there we have again the series. If n goes to infinity, then well, this goes to infinity. You just write that as the sum k from 1 to infinity of a sub k, which is again our series. All right. Now, assume divergence. Assume the integral is divergent.
Professor, why do we assume it's divergent?
Well, because I want to prove the divergence part of the theorem. I haven't proved that yet.
Makes sense. Okay.
Yeah, I used the previous inequality and I assumed the integral is convergent. For this one, we're going to assume divergent because that assumption is going to work. Okay, I can't use this inequality to assume divergence. Let me go back. So with this inequality here, I assume the integral is convergent, then we prove that the series is convergent. Yeah, we assume integral is convergent, and that showed us the series is convergent. But I can't use the same inequality to prove divergence. Guys, I hope you guys are listening with all you have. Okay, again, this stuff is tremendously important. So focusing on this, if I assume this integral diverges, then that shows nothing. Because if this diverges, then this is just infinity. And you get your series being less than infinity. Anything less than infinity could be infinite or it could be finite. We don't know which. So that shows nothing. Using this inequality and divergence assumption is just not going to work. Again, anything less than infinity could be infinity or it could be finite. Okay, but taking this inequality and assuming divergence is going to show that the series is divergent also. So assume the integral diverges, which means that the integral from 1 to infinity of f of x is equal to infinity. When in general an integral diverges, it means that integral could be infinity, it could be negative infinity, or it just doesn't exist. It could be some weird, like it could be both infinity, negative infinity, so we say it doesn't exist. Okay, but we know for sure, if I assume divergence, then I know for sure the integral is infinity because the function is continuous and it is above the x-axis. So area is always positive. That would be positive infinity. So now under this assumption, this inequality becomes, so for that we get infinity for the left hand, that would be infinity. And the inequality becomes the series being more than infinity. Look at that, guys. The series is bigger than infinity. So what does that say about the series?
It's divergent.
Yeah. Anything larger than infinity must be infinity.
Professor,
Yes.
will we ever have to utilize these proofs to show our work, or are the three tests?
We don't need to utilize these, no. Okay, so anything larger than infinity must be infinity. Okay. So what did we just show, guys? We showed that if the integral converges, then the series converges. If the integral diverges, then the series diverges. Okay, that's what we just did. So let's do more problems with the integral test. And again, I will go over what you need to show. And then we'll come back. Actually, you know what? While we are at it, let me show you something. Yes. let's do that because we have these inequalities right in front of us. So as I said, I know there's just so much I wrote down here. It could be a nightmare of notations for you guys, but please go over this stuff, guys. Go over it, okay? Do so. It's good for you if you go over these. Make sure you understand them. But where are we? Yes, this thing right here, guys. This. Why is this inequality? Let me tell you why this inequality is important. Let's say you're writing a computer program and your program does sums, okay? It computes sums. Like let's say you want to do the harmonic sum. Remember we talked about the harmonic sum 2 days ago and we said it diverges. If you were to add the terms long enough, you would get such blah, blah number. I don't remember. But let's say you want to write a program and you want to come up with with a bound. What your sum doesn't go above. You're going to use this inequality. Okay? It is highly helpful to kind of estimate sums. Like the harmonic sum. Okay, so this says that if I were to add terms of a series, like let's say if I were to add 1,000 terms of the series, 1,000 terms of the series, then the value of the series is going to be less than this expression. Again, you're getting an upper bound, and all you have to do is plug 1,000 here and integrate f of x, assuming you can't integrate f of x. So let's show you an example. This being less than a1 plus integral from 1 to n. This is called the upper bound of a partial sum. Upper bound of a partial sum. That is the upper bound. All right. Remember that scenario I was telling you about. You assume you can live as long as the age of this universe, and you can and you have to add the terms of the harmonic sum using a computer, using the fastest computer. Okay, so let's write down that scenario and do our calculation. So a supercomputer is used to add terms of the harmonic series for 15 billion years. So that's a lot of calculations. Okay, and I don't know how much the faster processor. So let's say that the fastest processor does 2 times 10 to the 7 calculations per second. It could be a little bit more, I don't know. I'm just assuming it's that much. Okay, we're gonna find the upper bound, find an upper bound. for the sum. Again, upper bound is the number that the sum is not going to go beyond. All right. So here you wanna figure out what n is. N is the total number of computations that you're gonna do throughout the period of 15 billion years using this much calculation per second. Okay, that tells you how many terms of the sum you're going to be adding. N is the number of terms to be added. Okay, so n, it is going to be, you're going to be doing this for 15 billion years. That would be 15 times 10 to the 9 years, 15 billion. Multiply that by, you're doing this every day. There are 365 days per year. Okay, every year has that many days, and you're going to be doing this 24 hours a day. Okay, so we multiply that by 24 hours per day. Multiply that by 60. You're doing this every minute, so every hour has 60 minutes, 60 minutes per hour. Times that by, there are 60 seconds. Per minute. Okay, because I gotta do this because this is done per second, right? This is the number of calculations per second. So multiply now that by 2 times 10 to the 17 calculations per second.
Isn't it 10 to the 7th?
Isn't that 7?
Is it 7? Yeah, 17 is just, I wish.
That's a lot.
I know, that is a lot. 2 times 10 to the 7. Okay, and yeah, so when you multiply all of this out, notice that the unit of years cancel, the unit of days cancels out, hours cancel, minutes cancel, seconds cancel, and that leaves you with the number of computations. Can someone do this on a calculator for me? Let me see. Yeah, would someone help me out with that? I have like 10,000 calculators in my house and I just can't find one right now. Sure. Let's do it on my phone.
I got an overflow error.
What?
I got an overflow error.
Oh, you did?
Yeah.
It should be, let's see here, 10 to the 9 times 10 to the 17, 9, 17. Should be 9 point, yeah, just doing this on my calculator. And I got, yeah, I got 9.46808 times 10 to the power of 34.
I
Let's
think
see if that makes
you
sense.
do 17.
Oh, I did use 17 again.
So
So 24?
yeah.
Yes, there we go. All right. Oh, thank you, Anna. Thank you so much. Okay, very good. All right, so this is how many terms of the harmonic sum you'll be adding. You'll be adding, so for 15 billion years that you run this calculation, you'll be adding this many terms of the harmonic series. Okay, so what does that mean? This is the harmonic series. your k goes from 1 to n, n being this monster of a number. Let me highlight that. Let's go with this color. Okay, so that's how many terms you'll be adding, terms of 1 over k. So your first term will be 1, then 1/2 plus 1/3 plus dot 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 plus 1 over 9.46808 times 10 to the 24. Okay. Well, that's because we can't, I mean, we cannot in practice do the sum from 1 to infinity. We just can't. And theoretic 1 to infinity is a theoretical thing. The actual sum from 1 to infinity, the actual value of the series, it is impossible to get that. We just can't, right? What we can do is limit it. And this is our limitation. Assuming you've had this fastest processor, you're an alien, you were born with the universe and you have access to this processor. This is our limitation. Okay. So this inequality here says, guys, if I have some k going from 1 to n, this is going to be less than the first term. And the first term here is just 1. A1 is 1, so it's less than 1, plus the integral from 1 to n, n being again that number. Of the function 1 over x dx. Why 1 over x? Why 1 over x? Because the sequence function is 1 over k. Okay. So do the integral and add 1s. We have 1 plus the integral of 1 over x is ln of absolute value of x, but here x is positive, so I'll just drop the absolute value. It's from 1 to that number. I'm just going to copy and paste that. Okay, so we're going to get 1 plus the natural log of that number. Okay, and minus ln of 1. ln of 1 is just 0, so I'm not going to write it down. And do this on the calculator now. Okay, let me see. Do ln. I'm going to punch that in. ln of 9.46808. And you can use properties of logs if you want it. So 10 to the power of 24. And I get 57.5. Yes, Anna is way ahead of me. I get 57.509. Approximately 5.1. So the answer here is 58.51. This is why we have no empirical evidence that the harmonic series is divergent. You're adding so many terms of this series, and the sum can't go beyond 58.5. So if you're gonna prove that this series goes to infinity by just plugging in good luck. You literally need to live forever to prove that. But a very, very, very slow series to diverge. And this just tells you you're adding almost forever, and this is what you get.
That also means ln is very slow, right?
It also, yeah, it also, yes, you can use the argument that this diverges slow to argue that ln is going to infinity very slowly. Yeah. So when they say, yeah, the harmonic series is divergent, okay, and you try to prove that by just plugging in, this is how much you get to. Okay, yeah, very slow.
I have a question. So,
Right. Question?
yes, so the 58.51 just means that that's the value that it cannot exceed, right?
Yes.
So I guess my question is, what's like this, like, you know how in previous examples, like we were like in the book, like for instance, like in 11.1, it's like, oh, if it's like convergent, find its sum. And then if it diverges, then it just diverges. But like,
Right.
I guess like for this like case where you have like the series being less than a1 of the integral, like how would we know if this series like diverges or not?
We
Like,
already proved the harmonic series is divergent.
right, but like if it was just like a random like series, like
Uh-huh.
would we use like the integral test first?
You can, you
okay.
can, yeah. You can use the integral test. The
Okay.
chance that we can use the integral test on a series is almost zero.
Okay.
Because integrating the sequence function is most likely undoable. Yeah,
And
but we're going to be establishing other tests that are way easier than the integral test to
okay.
prove the convergence.
And another quick question. So if the, let's say we get like the series like converges, and then we get that the series is like bigger than a1 plus the integral, uh, how do I say it? I think I'm kind of mixing like the upper bound and like the sum
Uh-huh.
of the, so if let's say like the series is convergent, the sum of the series would be different than the upper bound, right? Like that's not the same
Yes.
thing, right?
Yes, definitely.
Okay.
Yeah, you can always use this to find the upper bound of a partial sum. That's what we are doing. This is a partial sum, and we are saying that partial sum for this n doesn't exceed that. This formula is always true.
Okay.
Yeah, it regardless of the series being a convergent or divergent, you can use that. Okay, if the series is convergent and you can find its value, its actual value, then you don't need to find bounds, right?
Okay, yeah.
You don't. So, but for series that are divergent, you are interested in finding bounds.
All right. Cool.
All right. Okay, so let's do an example, and after that, I want to go over the P integral theorem. The P, not the P integral, the P series. The P series. But the example I want to do is this series here. Okay, going from 2 to infinity of, let's go with n, guys. N from 2 to infinity of 1 over n ln n. I had to begin n at 2 because when n is 1, you get ln of 1, and ln of 1 is 0. You get 1 over 0, and that would be undefined. Okay. All right, so if I were to expand this a little bit, I have 1 over ln 2, 1 over 2 ln 2 plus 1 over 3 ln 3 and so on. Okay, so first of all, everyone, you should always begin by using the nth term test. Because if the nth term goes to anything but 0, then you're done. The series is divergent. Okay, and you don't have to do any other tests. So do that in your head if you want. If not, write it down, because checking the nth term is typically easy to do. You just see what happens to these terms as n gets big and bigger. Obviously, the denominator increases. Therefore, the whole thing, the sequence itself goes to 0. Okay, check the nth term always. Limit of a sub n, that's the limit of 1 over n. This has got nothing to do with partial sums. This has got nothing to do with the actual sum. You're just checking to see what happens to the terms of the series, and they just go to 0. And this means that the series may converge, may diverge. The nth term test doesn't tell you anything. Okay, it would have been great if you got a number other than 0, because then we would say the series is divergent, but this is inconclusive. So we have to do a different test. It would be, again, this would be conclusive if we got, say, 1 to anything but 0. But that didn't happen. So next test that we know of is the integral test. And of course, you would try and see if the series is geometric. It's not. If it's geometric, if it's telescoping, then you could treat them that way, but this has got nothing to do with the geometric series. Okay, now for the integral test, I must check the 3 requirements. F has to be positive, continuous, and decreasing. So here we're gonna let f of x equal 1 over x ln x, because the sequence function is 1 over ln n, and it is going to be on the interval x greater or equal than 2, because here n begins at 2. We are on the interval 2 to infinity. Check that again, check the 3 requirements. First one says f has to be positive, and f of x here is positive. This is greater than 0 for x larger than 2, because when x is more than 2, more or equal to 2, of course, this factor is positive. And ln of x is going to be positive for x greater than 2. So this is because x is positive and ln x is positive for x larger than or equal to 2. If you graph ln of x has x-intercept at 1. After 1, it becomes positive, and it stays positive. Yeah, you can draw a graph to confirm that. Okay, x-intercept. After 1, it's positive. So since the domain of integration is more than 2, then on 2 or more, it's definitely positive. Nothing crazy to prove. Okay, second requirement says that the function must be continuous. CTS means continuous on, or for, I should say, x greater or equal than 2, because nothing on this interval makes this function undefined. Okay, the numbers that would make this undefined would be 0 and negative, and none of that is in this interval. Okay, ln is continuous. Ln is continuous function. That is a continuous function on 2 to infinity, and 1 over x is also continuous because 0 is not in that interval. Just mention it. There's nothing crazy to, again, to prove. Third requirement is f of x being decreasing. Okay, and for that, you can use the first derivative. Find f prime of x and show it's negative or eventually negative. All right, so here I have to use a quotient rule. I have to use the quotient rule, square the bottom, take the derivative of top, which is 0, minus the derivative of the bottom. Bottom is x ln x, and for that we use the product rule. Okay, the derivative of x is 1 times that by ln x plus x times the derivative of ln x, which is 1 over x. And I'm going to put that negative in front. We have negative of ln x plus 1 over x ln x squared. All right, and this is definitely negative, guys, because a denominator is a square. It's always positive. Okay, ln of x plus 1. Again, ln is positive when x is 2 or more. It's positive from 1 to infinity, but on the interval 2 to infinity, it's definitely positive. It's above the x-axis. Add 1 to that, it's even more positive. So ln of x plus 1 is positive. You have the negative of a positive. The result is negative. Okay. And yeah, you could justify by saying because 1 plus ln of x is positive and x ln x squared being positive for x greater or equal than 2. Okay. With the negative in front, the whole thing is going to be negative. And this means that f is decreasing. For x greater or equal than 2. All right, so all 3 requirements are met. That condition is met. This is met, and yeah, all 3 requirements are met, and you have to check all 3 of them. Now we can use the integral test, hoping that we can find the integral. We can find the antiderivative. That, again, as I said, that is the bad thing about the integral test. We most likely can't find the antiderivative, but for this function, we actually can do the antiderivative or the integral from 2 to infinity. Don't do from 1 because 1 is not in the domain. Again, everything begins at 2 because the index begins at 2. On 1 to infinity, the function wouldn't be continuous. The integral test wouldn't work. Okay, and that is the same as the limit. This is an improper integral. You must redefine using a limit. Okay, and we are going to do a substitution because If I let u equal ln of x, the derivative of that 1 over x is sitting in the integrand here, 1 over x. Okay, and I'll write ln of x in blue like that. So do u equal ln x. Okay, which means du is 1 over x dx. Okay, so this becomes, let me just do a separator here. This becomes the limit as t goes to infinity. Do not write down those limits of integration because we are changing the variable. We get 1 over u. Okay, and this 1 over x dx, 1 over x dx is just du. All right, change the limits of integration. Go from x to u. So all you have to do is substitute these x values into your relation between u and x. If x is 2, then u is ln of 2. The lower bound is ln 2. And if u is a t, then plug that into x. That's if x is equal to t, then u is equal to ln of t. Okay, now find the antiderivative of 1 over u. The antiderivative is with the limit in front. The antiderivative is ln of absolute value of u. Okay, and u here is going to go from ln 2 to ln t. Okay, plug in. We get ln of absolute value of ln t. Okay, minus ln of, plug in ln 2 for u. Yes. And now take the limit. You have a double ln. It's all right. It's fine. Again, you don't need absolute values there because t goes to infinity. So everything's just going to be positive. But double ln, which says that as t goes to infinity, this ln, every ln is just going to go to infinity. Now here's a graph of ln. Ln goes to infinity. So the argument of this outer ln goes to infinity. Please don't plug infinity in like that. But imagine there's an infinity here. And you get again ln as its argument going to infinity. This is still infinity. Okay, it doesn't matter how many ln is composed with ln. As long as the variable goes to infinity, the whole thing goes to infinity. And you're doing infinity minus a constant. The result is infinity. Okay. Yeah. So we are done. Our integral is divergent. Which means that the series diverges. Okay. Yeah. Guys, please don't forget to make a reference to the theorem, and that's by the integral test. All right. Any questions? So before we go, we have the P series theorem, the definition of a P series, and let me write it. I was going to do this tomorrow, but a P series, we'll teach this tomorrow. A P series is just like a P integral. It is the sum of 1 over n to the power of P. Okay? P could be 1, could be 2, it could be 3. So for instance, we have 1 over n squared, the summation 1 over n squared. We have the summation 1 over n cubed. We have the summation 1 over n, which is the harmonic sum. The harmonic sum is a P series itself. And just like the P integral theorem, we can show that a P series converges when P is more than 1. When P is more than 1, it converges, and if P is 1 or less, then the series diverges, just like the harmonic series. Okay, so 1 is the tipping point of convergence and divergence. Meaning that if this power is, like, let's say the power is 1.000001, if you have n to 1 point, no matter how many zeros are right, and then a 1, the series is going to converge. As long as the power is more than 1, it is convergent. Okay, so harmonic series is it. You increase the power by slightly, then it is going to converge. Now, think about this series, guys, for a second. Think about this. If I didn't have this ln n, then obviously this would diverge because it's harmonic. Putting this ln n could trick a lot of people. Writing that ln n in the denominator along with n might say that you're slightly increasing the power of the denominator. We already had this n. Now we make the denominator a bit more powerful by putting ln n next to n. So now the series is going to converge since the denominator is more powerful. The more powerful the denominator, the more likely the series is going to converge. So again, without it, divergent. With this, more powerful, therefore convergent, and that didn't happen. The series is still divergent. Think about that, please. So again, this was kind of against intuition. You make the denominator more powerful by putting an extra factor, then it is going to converge. That didn't happen. And that says something about how slow ln of n is. Really slow. It is so slow that, as I said before, it is almost powerless. It is almost powerless. This ln n, you put it there, it didn't do anything. It still made the harmonic series. It didn't make the series more powerful than harmonic. And it still diverged. Guys, think about what I said. Okay, think about it. Maybe when we do the P series tomorrow, it makes more sense, but think about how slow ln of n is. And I'll see you tomorrow.
Thank you, Professor.
Thanks.
Thank you.
You're welcome.
Thank you, Professor. Professor, I have a quick question.
Yes.